Hey, what's up, AP Calculus? Today we're looking at 3.2 differentiability. So let's start off with places we can't find derivatives. So we can't find derivatives if our graphs have corners. So notice that this top one, or this first one, is like an absolute value function. We can't find the value of the derivative at the corner. This is another version here. So it's a little bit more curvy, but same idea. We can't find the derivative at the point, and the reason why is that our slope coming from the left is a negative, and then going out is a positive. It's not necessarily slope zero if we're finding the limit as we approach from the left and right. So anytime we have a corner or a more extreme value of a corner, which we call a cusp, notice that it's going a little bit steeper as we go inwards. But same idea, we can't find the derivative at those corner points or cusp points. All right, the second type is if we have a vertical tangent, like we do here. So if it gets super steep in the middle where we go, and then we end up with an undefined slope, we can't find the derivative at that point. And the last thing that the last type of situation where we might not have, or we can't have a derivative, is at any discontinuity. All right, so let's go ahead and do some examples. The first one is asking us find all points where f of x equals absolute value of x minus 2 plus 3 is not differentiable. All right, so those of us who are good at recognizing family of functions and what the graphs look like, we know that this is an absolute value function, and any absolute value function is v-shaped. And then if you know this really well, we know that the transformation of x minus 2 just means that it's moved from the origin, the vertex is moved from the origin over 2 spaces to the right. So if you're just looking at this without even doing a calculator or a graph or anything like that, we could definitely say by our previous knowledge that this is going to be not differentiable at x equals 2. Okay, but let's go ahead and use our graphing calculators. And I know it's not the best way to from this photo thing. Okay, I don't know why it's coming out so pixelated on there, but it'll have to do. So what we're going to do is we're going to hit y equals, because we want to put in the graph of the absolute value. So we're going to do math. We're going to scroll 1 to the right to number, and we're trying to find the absolute value. We're doing the absolute value of x minus 2 plus 3. And then you're going to hit graph. And we can definitely see that the point, or the vertex where we'd have a corner, is at 2. All right, so let's go ahead and... Sorry, this is a little bit messy, but verify, yep, that's what we said. When x is equal to 2, then we're not differentiable. Okay, so for the next one, it says if f of x equals x cubed, use a calculator to approximate f prime of 2. So the cool thing about this one is we're not going to graph it, but what we're going to do is we're going to use the calculator to calculate the derivative. So let's go back here to our picture or our camera. So this is a cool function here. So we're going to hit math. We're going to scroll down to n derivative, which is 8, or you could just press the number 8. And notice that it's giving us like some weird symbol stuff here, right? So what we're going to do here is we're going to do d divided by, or d over dx, right? So what we're saying is we're finding the derivative with respect to x. We're going to put our function in it, x cubed, x, hit the caret to the third power, And then where it says x equals, that's where we put the 2. So we want to find the derivative of x cubed when x is 2. We're going to hit enter. And it's 12.000001. So the thing about the calculator is it uses the limit to find the derivative. So the real derivative here is actually 12, but it's got a little bit of extra decimal places because it can't, it used the limit, so it had to round a little bit. All right, so we go back here. We see that f prime of 2 is 12. Now we can also do it from the thinking that we used last time, right? So if we had to do this and it wasn't asking us to use the calculator, we'd use a power rule on x cubed, right? So we say we drop the 3 in front, we subtract 1 from the 3, and then all we have to do is f prime of 2 at this point. We're going to substitute the 2 in here. All right, so 2 squared is 4, 4 times 3 is 12. So the calculator mirrors what we have done if we applied our calculus and the power rule to the x cubed. Okay, so this next one, all right, so we're finding the n derivative, meaning we're using the calculator of absolute value of x at 0. Now, those of us who are good at the family of function stuff, we know that, well, this is the absolute value of x function, and we know that we have a corner when x is 0. So we're going to demonstrate here what happens. Back to our camera. So we're going to do math again. We want to find the derivative. So we go to math 8, derivative with respect to x, and we're going to do absolute value of x as our function. So we got to go back to math again. Absolute value, we got to scroll right 1. So that's our absolute value of x. And we want to see what happens when x is equal to 0. We're going to hit enter. And we find that it's 0. Right? So the thing to note about this, right, is just because our calculator gives us an answer here doesn't mean that's correct. So we need to be very careful about assuming our calculator giving us the right derivative all the time. So do not assume the calculator gives the correct derivative. So this applies mostly to if we have any non-differentiable parts. So this applies to cusps, corners, discontinuities, and vertical tangents. So be very careful. Just because you think that some function is going to have a derivative at a point because the calculator said so, be very aware that if it's located at one of those types of places where we can't find the derivative of that, it might not necessarily be true. Okay, and then the last thing to remember, and this is super important when we talk about continuity and differentiability. So what it's saying is differentiability, implies continuity. So what that means is if we know that some function is differentiable, so let's say this function here is differentiable, then we know that it's also continuous. right? So if we have a differentiability over the whole function, then we know that it's continuous over the whole function, right? Because if it's discontinuous, if there's some kind of jump or weird thing, then at that point, we're not going to be able to find the derivative of it. Now, the opposite is not true. The converse is not true. So the second part says continuity does not imply differentiability. So just because our graph is continuous does not mean that we can derive every single point on that graph. So the best example, or the easiest example, would be the absolute value function, right? So this is a continuous function, right? Over this whole function, we can trace it, and there's not going to be any gaps or any weird stuff. But it's not differentiable at the corner. Right? So this is an example showing why sometimes we could have a continuous function that is not necessarily differentiable, because we can't find the derivative at that corner. All right, so just keep that in mind. That's one of the things that's very important in calculus. They will definitely ask you about differentiability and continuity in some form on your test. So make sure you're very clear about continuity does not imply differentiability, but differentiability does imply that the function is continuous. Right, so pretty short today. Hopefully the calculator thing worked out. Sorry it's a bit wonky, but I think that's the best way for us to work through with our calculators and get comfortable with them, because you do need them for your test, and they're going to help you guys out a lot if you know exactly what you're doing. All right. Good work today. See you next time.